Okay, we left off here, and these two chapters, in some books, they're all one chapter. So they split it apart here, and we went through it kind of fast. And today's our last day. We'll cover new material before the next exam. So we'll just review when we get back from spring break. And I'm going to cover a little bit of the next chapter because these quantum numbers, the way they display it here is that there's 3 of them, but there's really a 4th. So we'll just go a little bit into the next chapter to explain the 4th. These 3 are the most important to the general shape, and all of these shapes are going to explain the bonding chemical bonds. Okay, let me put it full screen. Okay, so a wave function you won't hear again in organic chemistry. I mean, maybe once in a while or on occasion, but it won't be on the test or critical to it. You'd only hear this if you're a chem major or maybe a physics major. There's 4 of these quantum numbers. These first 3 are the important ones that give us the shapes, that give us the bonding and the way molecules look. You could just make notes and have this taped up on the wall. I'm not going to ask you, if you really want to, just to keep track of things or something during the exam, but I'm not going to ask you, N stands for what, and you have to pick the right one or something like that. That's silly. And you'll see as we go through and use them. So I know we already covered this. Just reminding you of those. Because that gets us to, those quantum numbers are important because they get us to how the electrons move, and the electrons are what makes the bonds, and then that gives chemicals their shape. Okay, so that wave function, right, the wave particle duality, excuse me, that we covered with electrons, they're going extremely fast, excuse me, near the speed of light. And so there's that uncertainty, right? The more you know about its location, the less you know about where it's going. And so we get these probability density maps of where the electron likely is. So I just need to move a block so I can see on my screen. There. And so these take on numbers of those quantum numbers, integer values, and then these letters. So it's introducing S here when we haven't quite told you what S is first. Yes, and anyway. But what this slide builds you up for, as you can see here, is nodes. And this isn't something just specific. Sorry. The term nodes isn't just specific to chemistry and electrons in this whole thing. It's a mathematical description of where something goes to 0. And in this instance, we're talking about the electron movement, these functions. And since it's the electron, it's where the electron is. The probability of that goes completely to 0. So, this is where an electron is, or an area under the curve where these 2 lines cross. That would be your node where it goes to 0. Okay, so the first orbitals and where electrons are first are what's called S-shaped, and they're spherical. Not, the S doesn't stand for spherical, but they're a ball, a sphere, right? And so this is supposed to be, X, and ironically kind of strange here, but X and Z would be in the plane of the board, and this Y-axis would be, say, going away from you and coming out of the board at you. And there is some, so then over here, probability density, and this isn't quite complete, but there's a maximum probability of finding it, and it drops off as you go away from, right, the 0 point is the nucleus, right? The origin is the nucleus. And we know from previous experiments, a couple chapters back, the electrons aren't in the nucleus. So that's the only deviation we'll see, and it's on the next slide here. This is a better picture. So that these s orbitals look like this, right? Where there's a 0% chance that the electron is actually in the nucleus, but it has some maximum distance. And this is sort of, again, similar to the way planets go around the sun. So this would be like Mars going around the sun, right? Mars is never at the sun, the nucleus, but this is its typical orbit distance from the sun, and thus the maximum probability of finding Mercury. That, you know, this would be that distance from the sun. So similar to the planets going around the sun. All right, so the L quantum number basically determines the shape of the orbital. And number-wise, for bookkeeping, the L can have these values from 0 up to n-1. And n is, we'll see, it's going to be the number in the periodic table. It's the row. So starts with 1 and goes on down. Then each value of L is called by a particular letter. So it's really, we'll see, the letter that's more important. And the letter tells you the shape of the orbital. And the shape of the orbital then tells you how it can bond. The S and the P are the two most important, and those are the ones you'll see in organic chemistry. D and F, we'll cover them here, but only higher chemistry classes. You'll rarely ever see them in organic chemistry. And you won't see these in Chem 162 either. So the D and the F. So the S and the P are a focal point, but while we're introducing them, yeah, you need to be aware of all of the ones that are possible. So S, P, D, and F. All right, so if L equals 0, that's what's called an S orbital. And it has this spherical shape, right? This is a little bit better picture than the last one. So you've got your ball, your spherical shape, right? These, a lot of times this is the jump between when everything you've seen in the book, in the chemistry world, is, you know, on a screen or a piece of paper or a book. It's flat, it's two-dimensional. You got to keep in mind that life is three-dimensional, and chemicals thus are three-dimensional. So X, Y, and Z, spherical. Okay, then again, like planets going around the sun, where the planet is, there's a maximum distance that the electron moves. So, you know, 1s we already saw. Now it's introducing the 2s, and it's further away. Right, so PM isn't time. This is picometers. Pico is times 1 times 10 to the minus 12. Nanometers is 1 times 10 to the minus 9. So it's an incredibly small distance, but we don't really care about the actual number, the actual distance, the numerical quantitative value. The point of it is, and then over here we see, you know, here's S3, S2, S1. And so relating it to planets going around the sun, where the cursor is here, that would be Mercury, Venus, and then Earth, right? Not the size of the planets, but this is the distance that their orbits go. Right, and so they get successively further away. And just like Earth and Venus never collide, electrons in the 2s and say the 3s are never in the same place. They never hit each other. These dashed lines you see here, these are the nodes. You'll never find an electron there. Just like the distance between of the planets from the sun, you'll never find any planet in between, say, Earth and Venus. All right, and here they just zoom in on it, right? So at the top is the wave function, and then the bottom is what you statistically see. So clearly we're going to move along to the next number up. So L was 0 for S. If L is now 1, that has to be denoted with a different shape and a different letter. These are called the p orbitals. And the next quantum number, called m sub L, can either be 0 or then the positive or negative value of your L. So that means it can be -1, 0, or +1. Each one of these m sub L numbers designates a orbital. So what this tells you, since m sub L has 3 possible values, then there's 3 possible orbitals, and they're all p's. Now, it turns out the way this works is that each one of these p orbitals goes along the x, y, and z axis. Right, it's second lowest in energy, and it has 2 lobes. A node at the nucleus, which means that there's a 0 probability of finding the electron at the nucleus, which we kind of already knew. And the 2 lobed basically means it kind of looks like 2 balloons tied together, right? And again, it's the y-axis one is the one that's a little tricky to see, right? So the x here is supposed to be in the plane of the board. So is the z, it's going up and down. But this y one, you would imagine sort of coming at you and going away from you. It has the same type of radial distribution, right? Distance from the sun of a planet, right, at its maximum distance. It's just that it takes on this shape, and it's a 2, so its distance from the sun is going to be kind of similar to 2s. And we'll see how that translates to the periodic table, and it's basically the row in the periodic table. Okay, so if you've kind of noticed the trend here, right? L for S, L was 0. For P, L is 1. D is the next one. L is 2 for D. The m sub L can always be 0. Then it can be plus or minus that, any of those L possible numbers. So -2, -1, +1, +2. Each one of these m sub L values denotes an orbital. So that means that there's 5 d orbitals. Now, this is where we're not going to focus as much on these, because these start to get more complex, and the F ones, the next ones, are going to be even more complex. We've moved along, so it was lowest and second lowest. This is third lowest. And you'll see the shapes on the next slide, but they kind of are 4-lobed, but they're a little different. They're more complex. All right, so here's what they look like. This donut looking thing here is called a toroid, but they're basically the 4-lobed. These are only important, the shapes of them, I mean, for using them in higher chemistry classes. You won't see these again in Chem 162, and you'll barely see them in organic chemistry. So I tend not to focus a lot or put a lot of things on an exam that you won't see again in future classes, right? A big part of this is to prep you for Chem 162, and really these last couple chapters are important for bio majors that are going to take OChem, because we're getting there, but it's going to be chemical bonding. Okay, so the trend continues, right? The L number increases, 0, 1, 2, now we're at 3. We move up to the next letter. It happens to be F. And the same trend in our m sub L number, right? 0 is always there. And then L can be plus or minus 3, plus or minus 2, plus or minus 1. Each M sub L number designates an orbital, so that tells us there's 7 possible d orbitals. Okay. And we've moved along fourth lowest energy. And not too surprisingly, now it's kind of done the same trend, right? We went from the spherical ones to 2 lobes to 4 lobes. Now these ones are mostly 8 lobed, but there's, it gets more complex with a toroid. A planar node just means that it's not just one point like it was before, but that there's a whole plane where there's no electrons. Okay. These orbitals are even less important in the world of chemistry. I don't like the D ones I have memorized just from using them so much over the years. These I've never used, and most chemists on Earth don't use these very much. So you definitely will not be tested on knowing the shapes or the X, Y, Z axis labeling here. I don't even know if that would be in an upper division, maybe in a grad class, chemistry grad class, and then even then you don't use it much. Okay, and so what this is trying to put together is, here's sort of what's important is what we care about is the nucleus is there. This is where the electrons move, and the electrons are going to combine using these orbitals because that's how the electrons move and make bonds. And when you put all these together, they overlap and you basically get a spherical type of shape. All right, slide 73 summarizes everything we just looked at here. So principal, level, and that's basically the row in the periodic table. And it'll make sense when we see a couple periodic tables coming up, how they label these. And one of the key things here is that when you move from 1 to 2, you don't lose the, let's say, the S here, right? So in n equals 1, you only have the S. When you move to the second row in the periodic table, you have S, P. When you move to 3, you have S, P, and D. And what's left off here, because the F orbitals aren't terribly important, when n equals 4, you'll then have S, P, D, and F. But, it's not even included in the slide because the F orbitals, they're just not used very much. Okay, again, the book splits up this chapter. Some books don't split this chapter. It's just what these slides in this book did. So we'll just go a little bit into the next chapter because the concepts go together where we get to the bonding. So, and we'll come back to those orbitals. We'll need all those later. Okay, so Mendeleev, we saw this name already. He is basically the father of the periodic table. So what he did was he started ordering these elements by their atomic mass. Then he saw a repeating pattern, and this became periodic law. And so you can decide when and how to arrange them, and you put them, and so he arranged them so that they would have similar properties in a column. And then he used these basically to predict things, elements that he hadn't observed. And this is basically like if you've ever played around with when you have to turn in a paper, they tell you how many pages. If you mess with the font or the margins, you can change the length of the paper that you're writing, right? And basically, you type it out, and then if you move the margins in, right, it changes where the sentence ends on the paper you're writing. And that's basically what he did. He started to put these all in a row, and then he noticed at certain spots, if you made the margin here and started over, the elements started to line up and have very similar properties. And we already looked at the periodic table, so some of this we've already seen where we did the naming the ions, right? So group 1 always had a +1 and group 2 had a +2, and the elements took on similar oxidation states, gained and lost electrons. The metals all ended up, basically to the left, and the non-metals all ended up in the far right. Some of these things you haven't covered, acidic and basic oxides to know what they are. Okay, so one of the classic examples of this is that he predicted elements that he didn't know of. So these two, Ga is gallium and Ge is germanium. And here you see his prediction. So he knew the element above it and below it, and made a prediction on what these two elements that he hadn't found yet, where they would be. And lo and behold, they came up pretty close, and this was a long time ago. So the kind of things that you could measure were not really high tech, like density. We didn't have computers. Mendeleev, I don't even know his birth and death, but it was a long time ago. So density was one of the critical ways of identifying what something was, and this was how they identified gold, especially a long time ago, was very dense, and to make sure that someone just didn't try to sell you a piece of lead instead of gold. The density was unique and indicative. All right, so this periodic law allows you to predict the property of an element based on its position in the table, which we've already started to do, but it doesn't explain why the pattern exists. That's what the quantum mechanics and those quantum numbers that we introduced last chapter do for us. Okay, the last quantum number that wasn't there has to do with the spin of an electron. So again, it's not a history class. So Stern and Gerlach are the two that discovered this, and they're basically using a magnetic field. They set up this experiment that electrons actually spin on an axis. And then when you have something that's electronic and it's spinning, it creates a magnetic field. And so then we get to the issue of the number of electrons, right? And if you have an even number, about half the electrons will have this magnetic field that's north and south. So if you've ever played with magnets before, a lot of times, or they have, a north and a south. And so here's just a crude diagram of, what this looked like. So this is, again, you need nuclear radioactivity for this. And it's the same kind of setup we saw before, with like a metal box with a little hole for it to come out, and then like with the light, a slit to focus it. And then if you have a magnet, you also have to have some way to observe it. It should go straight through if it was neutral, but it wasn't, and they were seeing this type of pattern, evenly split, but up and down. So one has to be attracted to it and then repelled for the other. And basically what this gets us to is this idea that there's a spin up and a spin down to electrons, right? The electrons are moving, they're negatively charged, and they're spinning. And so the way you denote this is with a single arrowhead in the up or down fashion like this. I lost my animation from there. All right, so it's very typical in nature that if you can, things tend to be symmetric, and in this sense, they pair up and the spin gets canceled. So you've already noticed this, that a lot of nature tends to be symmetric, right? Our as humans, we're pretty symmetric. You have two hands, two nose, two eyes, etc., two nostrils, etc., etc., etc. All right, so these spin values get half values and a positive and a negative. All right, as we continue here, quantum mechanics is very P-chem, is very physical chemistry, basically really physics. So we have another name, and the only time these things help is like if you're on Jeopardy or that show, The Big Bang Theory, you hear some of these names. Pauli's another famous physicist. The exclusion principle basically is saying that no two electrons in an atom have the same set of all four of these quantum numbers. So every electron is unique, sort of like, I don't know, a snowflake or something. All right, so no orbital may have more than two electrons, and they must have opposite spins. So you can kind of think about them like your shoes, right? When you have a shoebox, or you buy a pair of shoes, they come in a box, that would be your orbital, and there's two of them, and there's a left and a right. So for us, it's spin up and spin down. And since there's two electrons in an orbital, the s orbital then can only have two. The p had three of those orbitals, so there's 6 electrons. The d has 5, so 10. The f has 7, so 14 electrons. So then here's, the last slide on the last chapter. This is basically, that one's was kind of graphical. This one's more in a table form and has them by their name and their values. So the principal number is basically the row in the periodic table. The L is 0, then plus or minus whatever the principal number was. The magnetic, the L was 1 minus the N. The L is plus or minus whatever the L number was. And then the spin is either just plus or minus. All right, and then what these do, N tells us the distance from the nucleus. L tells us the shape. Was it S, P, D, or F? The M sub L, the orientation of the orbital. So that would be really what, it doesn't really apply to S, but what we care about mostly is P. So P had X, Y, and Z, and only 3 of them, so X, Y, and Z. It was more complicated for the D and the F, and so we won't care about those. Then for the M sub S, it's up or down, like left or right, and it doesn't really matter. If you have one, it doesn't matter. Typically it's labeled as positive first, and then the next one's negative, and they cancel each other when it's even, but it doesn't really matter. It's understood that there's only one there. And whether something is, top or bottom, spin up or down, is depends on your point of reference. So like, if someone gives you a soccer ball and asks you to point to the top, right? It's perfectly spherical. There's really no top. It just depends on your perspective. Okay, so let's start and go through it and relate it back to the periodic table. Helium, for example, is the second element. So it has 2 electrons. It's in the first row of the periodic table. It's the second element. So its N is 1. The L number is N minus 1. So that's 0. The M sub L, it can't have a positive and negative number because it's 0. So the M sub L can only be 0. And then here's where all 4 quantum numbers can't be the same. So 1 electron, and conventionally you put a plus in there for the first one, plus 1/2, and then minus 1/2. Right? So electrons with very similar, all 4 quantum numbers are going to be similar in their location and shape and etc. And the only difference when they're in the same orbital like this is the spin up and spin down. So what this is getting us to is electron configurations, which is basically a way of describing the number of electrons associated with an atom. And ground state is the lowest energy. And so let me just go back. So ground state something like this, right? This would be the ground state. So if you remember back to last time, a firework basically works like this. You know, it goes up in the air and it explodes. The explosion gives it enough energy to raise the electrons. And then as long as there's an empty spot down here, n equals 1 is the ground state. So these electrons are all going to move back down to the ground state if they can. And we'll see that this is kind of similar to if you've ever heard of the game Connect 4. And while we're at it, let me just do the Google images so we're all on the same page here. And so if you've never seen this game, I don't know how old this is. It's old though, right? You can tell by this picture that it's kind of old, but this looks a little newer. Anyway, this one's obviously like these big ones. Anyway, the point of it is the ground state would be gravity's pulling down, just like in a nucleus, in an atom. The nucleus is positive, the electrons are negative. So it's always pulling the electrons towards it. And so as you drop these in, they drop down. And the electrons kind of do the same thing, where an electron does it, you know, just like this little puck or chip or whatever it's called. It doesn't levitate up here, it falls down. And it can only go where there's an empty spot. And the electrons are going to do the same thing. Oh, sorry, Ben. When I change the shares, it moves around the chat box. I just saw uh, your comment there in the question box. Yeah, so the second electron denotes the difference between helium. The first electron, yeah, would just be hydrogen. All right, let me get back to full screen. Okay, so that's the ground state. The distribution of the electrons in various orbitals in the atom in its ground state is called the electron configuration. So it's where all of the electrons that the element has that the number off the periodic table is in the orbitals that are closest to the nucleus. The number designates the principal energy level, so that's the row in the periodic table. Right, letter tells us the shape, and so that's the type of orbital, the S, P, D, and F. The superscript designates the number of electrons. And so you don't need to, since the spin is either up or down, you don't actually need to indicate that. It's obvious because we always understand that the first one put in would be the spin up or positive, and then the next one has to go spin down and they pair to be opposite. So helium, first row of the periodic table, that means it's an S with 2 electrons. So 1s2 means helium, right? The equal sign, and helium in the electron configuration world means 1s2. So this writing 1s2 symbolizes the same thing you see here, right? It's a shorthand version of telling you all this information. Another way of showing it is visually with these diagrams. So here we have an orbital, and they denote it like a box. So this is kind of where I make the analogy right back to shoes. The box is empty, there's no electrons. You put one of them in, we always put the arrow up, and it doesn't matter whether the arrow has two heads to it here or just a half an arrowhead. It doesn't matter. Everyone knows in these descriptions that it's an electron. And then the second one has to be paired down because it's got the opposite spin number. So plus 1/2 minus 1/2. So empty, half filled, and filled are the only options. Okay. The sublevels in a principal energy level diagram. And hydrogen is the simplest one. If they're the same in energy, we call the orbitals degenerate. Just kind of a strange term, right? Doesn't really overlap with the general meaning of this, but it means they're equal. And we'll see this coming up, good examples of it. And, again, to the Connect 4 example, it means they're in the same row and there's no difference between them. So if you have, like, say, two p orbitals that are empty, they're the same in energy, then they're degenerate. Right, for multi-electron atoms, the energies of the sublevels are split. We'll get to that. And there's a little subtleness here, so keep in mind that these electrons are negatively charged, so they repel each other a little bit. And it's a small repulsion, but it's enough to see some behavioral differences. The lower the value of L, the less energy the sublevel has. Right, so SPDF. And this all makes sense here in a couple of slides. Okay, not a terribly important concept, the penetrating anyway, but the shielding kind of is. So what this is going into is kind of the way an umbrella shields you from the rain. The further out an atom has orbitals and electrons in it, those will shield the inner ones, right? So if you've ever peeled an onion, it's layers, right? And the outer layer shields the next layers in. And you can't get to, kind of like an apple as well, you can't get to the seeds, the core of the apple, without breaking the skin, right? The skin is the outermost portion, and it shields the rest of the core. And that was real wordy. I don't want to read it all to you when the picture explains it much better. So this is showing you lithium. Lithium's the third element, so it has 3 protons. So lithium metal has 3 protons and 3 electrons. The first 2 are in the s orbital, right? And they're closer, and they're this distance that you see in blue. The next electron is in a further orbital out. So you can think about these 2 electrons here being, say, Mercury, moving around the nucleus as the sun, and that this next electron is Venus. Right, so you can kind of ignore the penetration. It's just introducing that concept here because it's the exact opposite of shielding. But penetration only happens when you have a nuclear reactor, so not really, doesn't have as big of an application. But the shielding becomes important. So, right, there's a 3+ charge from the lithium, and the 2 electrons here are kind of like an umbrella, and they cancel out 2 of the 3+ charges. And so this outermost electron, it's kind of like it only feels a +1 charge instead of the +3. So the inner electrons, which we'll see is called the core, And all of the electrons that we're going to care about are just these outermost ones, the ones that are in the outermost shells. Those are the ones that leave the atom to make the ions that we saw and talked about a few chapters ago with naming. So these core electrons do the shielding and they don't go anywhere. The outermost electrons, which are called valence electrons, those are the ones that move to and from atoms and do the overlap to make bonds. Okay. Now, this is real typical in the world of science where we introduce a concept and try to make it real simple. And then once you start to learn it, we tell you it's a bit more complicated than first shown. So I made the analogy, go back here. I was making the analogy like Connect 4. Let me just go back to that. And that's too simple of an analogy, right? And here, you know, let me pick whatever. I'll pick this one, whatever. You know, n would be the bottom row, n equals 1 is the bottom row, then 2, then 3, then 4, etc. The problem is that once we move up from n equals 1, where there's just the one s, we get s and p, then sp, d, and f. And the sp, d, and f are not all the same in energy, so they don't make a perfect grid like this. What they do is they make a more complicated picture like this. So the 1s, there's clearly a difference between the 1s and the 2s, but then it turns out the 2p is actually higher in energy than the 2s. The 3s is higher, but it's kind of close to the 2p, right? And the 3p isn't the same as the 3d. The 3d is higher than the 3p. And then here's where it gets a little tricky. The 4s is really close to the 3d, and in fact, it's a little lower. And this is starting to look like an upside down version of the periodic table. So if you took the periodic table and sort of turned it upside down, because this is energy, you know, as distance from the nucleus, this is sort of what the periodic table looks like. And we'll see that this correlates directly to the number of elements in the different blocks on the periodic table. All right, so, you know, there's a little bit of difficulty with penetration, right? The sublevels are not degenerate. And the sublevels again means like SPD, right? The SP and D of 3 are not degenerate. They're not the same, right? All 3 of these P's are the same energy. So you would say that the 2 P's are all degenerate, but the 2S and the 2P are not degenerate, right? All 5 of the 3D orbitals, they're degenerate. They're the same energy. But they're not the same as the 3p or the 4p or even the 4s. And what's also important is the distances, the energies here, the gaps are bigger the closer you are to the nucleus. And as you get out further, they start to get closer in energy, and telling the difference between them is more challenging. Penetration of the 4th and higher levels is so strong that their S sublevel is lower in energy than the D sublevel of the previous energy. So that's a wordy way of saying this 4S is actually lower in energy than the 3D. Right? And so the 5S is actually lower than the 4D, the 6S is lower than the 5D. The energy difference between the levels becomes smaller as you go higher up. And you can see that. You don't really need, you know, this bullet to tell you that. It's just pointing it out. Slide 18 here, this will just depend on if you like the last picture or if you find that still confusing versus the periodic table. And this is just a way to do it where it's got this animation. So the way the energy wise, that we saw it on the last slide goes like this, where 1s, 2s, 2p to 3s, 3p to 4s, then 3d, 4p, 5s, 4d, 5p, 6s, and so on. I personally don't need this or care for it. When I was learning it, I liked the last slide, and then you'll see as we relate it to the periodic table how it kind of starts to make sense. All right, so this is where it's the good analogy, like Connect 4 and especially 2 slides ago. Imagine you dropped in an electron in the Connect 4 game. It can bounce around here and go to all these, but if there's no electrons, it's going to go down here into the 1s. And these can all handle 2 electrons. So if you put 2 electrons in, it's going to go here. Right, then like we saw on the last slide, they'll be at the 3rd electron is going to go here at the 2s. Right, the 4th electron goes to the 2s. Then the 5th electron goes to 2p. It's got to fill up the p's. Then the 3s, and et cetera, et cetera. So again, from lowest energy to highest, the subshells, if they're the same subshell, like all the 3p's are degenerate, they're the same. No more than 2 electrons in an orbital, right? That's all 4 quantum numbers are different. And then when you fill the orbitals that have the same energy, place 1 electron in each before completing the pairs. This is called Hund's rule, another famous physicist. And basically, my analogy with this is imagine, a family of 5 parents and 3 kids move into a home, and there's 3 bedrooms for the kids. They're each going to go in and take a room to themselves. They're not going to go into one room and get bunk beds and things like that. And the electrons do the same thing. And you'll see an example of what I mean coming up. Okay, so let's do one of these. Electron configuration for magnesium. Right, you go to where magnesium is on the periodic table. The number of protons is 12. So we'll have 12 electrons. 2 electrons go into each. So we're going to need at least 6 orbitals. 1s, 2s, 2p, 3s, 3p should do it. And start putting in the electrons. Right, so 1, 2, 3, 4, and then here again, 1 at a time until you have to pair them up, because they're electrons, they repel each other. So they're going to repel each other and be singles until they have to be doubles. And then there we get to 12 electrons. So that's magnesium ending with 3s2. Right, and so the outermost electrons are what are called the valence. We'll see that term coming up. And then the inner ones are the core and have the same configuration of the noble gas above it in the periodic table, which for magnesium is neon. And since the core electrons from 2p6 over don't go anywhere, they always stay with the atom. There's no reason to write them all out, so we can do this shorthand notation. All right, valence electrons are those outermost ones. Core electrons are the noble gas. They were in the brackets. These core electrons never go anywhere. The valence electrons are the ones that move. That's where we got those charges that we had for the cations and anions way back a couple chapters ago with naming and canceling charges. And those are the ones that move and thus give all the different atoms their chemical and physical properties that we see and observe. So here's just a few more examples. Krypton is a noble gas, so it always ends over with P6, right? You just start moving along on the periodic table in the order of increasing energies till you get there. And this one has the 8 outer valence electrons. When we move over 1, you add another proton, another electron, then that noble gas becomes the core of krypton, and there's only 1 extra electron. And this was why everything in the first row, the first column or group of the periodic table had a +1, is because there's only 1 electron there that's the outermost valence electron. And you can come up with the quantum numbers for all of these. I'm not too big on having you know the quantum number for every electron. That just explains the behavior that we see. But this single electron, the last electron, the valence electron, would be, in row 5. It's in the S, so the L must be 0. The M sub L has to be 0, and then formally we always put +1. This is just reminding you of what, I don't know why it's saying 2p here. That's kind of strange, but it's just reminding you of the possibilities for the 2p, which will be important in coming chapters. All right, so here's a combination, right? The element, as we move across the periodic table, the number of electrons, where they go, right? You fill up the 1s2, that's helium, right? Then we're moving across the second row in the periodic table, 1 electron at a time. You fill up the S and then move on to the P. The P's are identical, so 1 at a time, right? They repel each other slightly because they're negatively charged. The group number corresponds to the number of electrons, the length of the block, maximum number of electrons in the subshell, and the period corresponds to the, again, that principal energy level of the valence electrons. And so here's where you could fold the periodic table over. So if this was a piece of paper, you could fold it here and put element 4 and 5 together, right? And so the periodic table, this is why sometimes you could have helium written in here above beryllium in the electronic bookkeeping. And then reactivity-wise, sometimes hydrogen should be right here above fluorine, right? Hydrogen and helium are strange because of their location, and so unique that they're the only ones using the 1s orbital. And so, right, the S, only 2 electrons, and there's only 2 groups. The P, 3 orbitals, 2 electrons in each, so 6 elements, because 6 electrons, right? D, 5 orbitals, 10 electrons, F, 7 and 14. So this is why when you Google search images, the periodic table, you get so many different pictures, is because there's a lot of different ways to look at and think about the periodic table. So this is a good slide too, sort of labeling everything. This is, the P6 is a little off. This S2 should be up above. The P6 could be there, that type of thing. But S, P, D, and F. All right, so the way you show the electron configuration for any element, you find that element. This one's doing phosphorus. The core is the noble gas above it, before it, so neon. And then move across till you get to that element. So here's row 3. This is the S block, 3s2. We don't have any d electrons. We get to the P block, and we have 1, 2, 3. So the correct shorthand configuration for phosphorus would be neon in brackets. That's our core. 3s2, 3p3. How many valence electrons does it have? You add the outermost electron, so that would be 2 plus 3 is 5. On your periodic table, the transition elements or transition metals, since they're all metals, is that D block. That's the yellow portion of the periodic table, right? The transition metals or D block elements, those are kind of interchangeable terms. But it's the same concept, is that you get the noble gas above it and then move over to the row in the periodic table that your element is at and just march across. So zinc, for example, let me go back. Zinc is right here. So 4s2 and then 3d10 all the way across. Right? There's the 4s and the 3d. And so since those energy level splits are a little different, like we saw, the 4s comes first before the 3d. So there's this single number contraction. The F block does the same. We won't use the F block much, but technically this is the correct way to do it. So europium, for example, you find it, it's in period 6. You get the noble gas above it in period and row mean the same thing again. So in period or row 5, and then just move across in the periodic table till you get to whatever element, and this is EU, europium. So 6s2, and then the electrons want to be unpaired. And we'll see later coming up how unpaired electrons are really important for medical imaging. All right, here's another example. It's doing arsenic, As. Your core is the noble gas above it, argon, and then move across through the periodic table till you get to the element of interest, this one being arsenic. So 4s2, 3d10, and now 4p, and we're 1, 2, 3 elements over. So our core, argon, our valence 4s2, 3d10, 4p3. Valence electrons, you might initially think 15, but the valence electrons is just the s and the p orbitals, and that'll make sense in a couple chapters. But for now, just note to self that valence means however many s and p orbitals added together. Ignore the d's and the f's. Okay, so just a couple other examples. Sodium, so 11 protons, 11 electrons. Te is tellurium 52. Tc is called technetium 43. Whoops. So the noble gas above it. Sodium is over way on the left. It's in the third row of the S block and the first element. So noble gas and then 3s1. Te is below oxygen in the P block. Krypton is the noble gas above it. That's our core. Move across. So fill up the 5s, fill up the 4d, and you get to the 5p. Technetium is number 43. It's in that same row, so same core, but it's only the 5th element over in the D block, and they need to be unpaired. All right, so these properties of these elements in the columns have very similar chemical and physical properties because they have the same number of valence electrons. So the noble gases are all filled. They all end in P6, with the one exception of helium, but helium has its only orbital filled, completely filled. And things with filled orbitals are very non-reactive, right? You've been at a kid's or someone's birthday party before, and or seen it at least. Someone opens a balloon of helium, breathes it in and out, and it doesn't react. It doesn't do anything, right? So things that have full electrons, full p orbital electrons, are non-reactive. Group 1 all has 1 electron. And this is why you can't get, you're not supposed to have lithium batteries on, on planes and being, it's hard to get them shipped to your house. If anybody's had their phone or laptop break and you need a new battery, it can be kind of a pain to get because, and also, electric cars and stuff, anything high tech, lithium is really light, so they make batteries out of it. And it's protected, encased in plastic, but when it gets broken open, lithium wants to give up that electron, and giving up electrons is like electrocution, right? And can cause fires, right? You don't take your keys and stick them into a light socket, the electrical socket in your house, you get electrocuted. It's not quite the same. As you move down, things get less reactive, which we'll cover later on, but the electron count is the same. And so as you move down, these elements below lithium, they do similar chemistry, but we don't use them as in batteries because they're getting heavier, right? The reason we use lithium is it's so light, right? Nobody wants a heavy laptop or a heavy electric car. You're trying to go somewhere, a heavy laptop, a heavy phone, etc. The halogens, they all do the same thing. It was a -1 charge, right? And it's because they have 1 electron spot open, and they want to gain 1 electron to get to what the noble gas had. They want to go from P5, regardless of the row, to P6. Let me take a little evaluation here. Yeah, just a couple more slides. Okay, so the number of valence electrons basically determines the way an element behaves, and I kind of pointed some of those out. So the number then follows this periodic trend, and that the noble gas then became the margin on, if you think about the periodic table as a paragraph just written out, they wrote it out in a straight line. You decide where to set the margins and have a new sentence start over, and they did that at the noble gases. These quantum numbers are where we got how we oriented it, and they show that filled p orbital gives you 2 from the s and 6 from the p, and so 8 valence electrons gives you the noble gases in a very unreactive atom, right? The noble gases. You've breathed in, probably done it before, breathed in helium in and out. So elements that have either 1 or more, 1 or less electrons than the noble gases are pretty reactive, and that's the lithium, batteries and those halogens, right? They want to give an electron or gain an electron. The group 1 wants to give it up and be like the noble gas. The halogens want to grab an electron from somewhere. And that gets us to the charge that we saw, and you might have already written on your periodic table, if you had a periodic table like the one that I sent out and made notes on it, right? And so our groups translated on the metal side, group 1 was +1, group 2 +2, and then conversely, 6 and 7 -2, and then -1 to get to the same charge as the noble gases, right? And these were the typical ion charges that we saw. Boron's not up here because, a lot like hydrogen and helium, it's so high in the periodic table, it's a little strange, right? Carbon's not in here because carbon's right in the middle, so it can go potentially +4 to -4, right? It's the same number of electrons coming and going. We'll cover that in greater detail. And then, a few of these elements are left out because these are the metalloids where they behave somewhat like metals and somewhat like non-metals. The trend starts to change. Okay. I think I'm going to stop there. I hope, I went a little bit slower here than we did last time, because last time was just, a few math calculations on understanding the wavelength of light and refraction, just to get us to these quantum numbers. And then we're going to do these quantum numbers and build them up and make bombs coming up. But that's enough for new material. Just move stuff around. Okay, there. So as usual, I hit the unmute. So if you questions, comments, thoughts, feelings, whatever you want to talk about or ask, if you're good, then feel free to sign off, and see you after spring break. Monday we'll do the usual sort of review before an exam, the study guide, and if we have time, which we probably will, once we finish the study guide, we can go do some of those worksheets like we did last time.
Alrighty, have a good spring break.
Yeah, you too. Enjoy yourself.
Thank you, Professor.
Yeah, you're welcome.